Hey everybody, this is Siobhan, and welcome to another concepts lecture where we're going to be talking about the basics of vectors and why they're useful inside of games and how we can use them. Okay, let's start off by typing the word vector. Okay, vector, and some of you may have already heard that we can use them for position, and some of you may have also heard that we use them for direction. How can they both be used for position and direction? So let's talk about that just for a second. So we're going to have to rewind back to our geometry days, or I guess depending how old you are watching this video, we might be rewinding forward. And we have our kind of like XY axis graph here, and I don't know, something benign like an apple, unless it's poisonous. And let's say it's at a position of 2, 3. Okay, we understand that as this ordered pair, it represents its position, right? That position is also represented in games as a vector. Okay, so this would be a two-dimensional vector which has an x and a y value. So the apples vector would be something like 2, 3. The 2 represents the x position in space, and the 3 represents that y position in space. All right, okay, so and let's also create a banana. Here's our banana. Does that look like a banana? Hopefully. And let's say that the banana is at a position of 5, 7. Is that believable? All right, so now we have another vector, and it's banana. Too many nans. 5, 7. Okay, right. So this is how we can understand vectors, at least with respect to position. But how can we use them a little bit more powerfully than that? And one of those ways is, what if we wanted to determine what is the distance between the apple and the banana? Well, fortunately, fortunately, vectors can be just added and subtracted super easily. All right, so if we were to subtract the banana vector, we didn't even say vec, whatever, banana, which is banana language for banana vector, minus the apple vector, then what do we get? We get a value, it's 5 minus 2 is the x position, right? So this x component is 3, and 7 minus 3, so 7 being the y component of the banana vector, and the apple vector is 3, gives us a difference vector of 3, 4. So is a difference vector like special? It really isn't. This vector, which we use here, which represents the distance between these two, the difference of these two positions, is exactly the same as our other vectors. Because if we think about it, the apple's position 2, 3 is really just the difference between the position 0, 0 and 2, 3. Okay, and the position 5, 7 is really just the difference between 0, 0 and 5, 7. So ultimately, it's exactly the same thing. But how is this useful? Well, what we want to do is we want to know how long is this vector. Okay? In fact, that term long we can represent here as the noun length, and also magnitude. Magnitude and length mean the same thing when we're talking about vectors. It's just talking about how long is the vector. Well, how do we know how long the vector is? Well, it's really just a simple geometry problem that you may have remembered from back in your geometry days. Hopefully your geometry days aren't over. Maybe your geometry days will just continue forever. All right, and look, it's a right triangle where the horizontal, or the, I guess you're talking about your adjacent and your opposite and all that kind of stuff. But the x component of this right triangle we'll just use is 5 minus 2, it's 3. And the y component here, the vertical difference between these 2 points, is 7 minus 3, which is 4. Okay, so how do we get the length of this side, which is the hypotenuse? Remember hypotenuse? I don't know if you remember that, but you use the Pythagorean theorem. Yay! A squared plus b squared equals c squared. I don't know how to do superscript on this. All right, a squared plus b squared equals c squared, where a is one of the sides and b is one of the sides, and c is the hypotenuse, always represents the hypotenuse. So to get the length of the vector, we're simply getting the square root of the one side squared plus the other side squared. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. What's the square root of 25? Well, the square root of 25 is 5, which means then that the length of the vector, which is the difference between the banana and the apple, is 5. Okay, and now we know that the apple and the banana are 5 units apart from each other. And you can think of units as feet or meters or centimeters or game space units. It doesn't really matter. The point is that the length of the vector can be determined this way. And why that's useful is potentially in a game, let's say that this is a game where it's called like Night of the Scary Bananas, and you're trying to run away from the scary banana, and the banana only knows you're here if you are 5 units away. And so you can use this vector's length to be able to determine, so the difference between their positions, and get the length of that vector to determine how far away the banana is from the apple and whether or not the banana, the evil scary banana, can chase you. Okay, right? That's pretty useful. But let's talk a little bit more about other ways that vectors are useful. So right now I showed you how you can add and subtract vectors very easily. You can also multiply vectors very easily. So for example, let's consider a game that takes, the up and, well, let's do WASD, okay? Because those up arrows and what was that? Those up arrows and those down arrows can be kind of like misleading because you'll think I'm talking about vectors, but I'm just talking about like a letter on a keyboard. WASD, right? And so the input system of these game engines will often represent A and D as +1 in the X direction horizontally and -1 in the horizontal direction, and S is -1 in the vertical direction, and W would be +1 in the vertical direction. Okay, so far you're like, okay, I think I'm following you, but so there's a number of different types of games, like a platformer game, or maybe a first-person perspective game where you're moving around, or a third-person perspective game where you're moving around using the WASD keys. Okay, well, 1 unit sounds like very slow, right? If you want your character, and I guess we have our character, it's called like Apple Hero. It's like, anger apple, something like that. Our little character, it's got to have like, arms. Come at me. All right, and so your little anger character can move in different directions, right? In it's essentially 360 degrees in all sorts of directions. But you have to use these WASD keys to move. Okay, so if this character wants to move this way, then, well, if you hold the D key, then that's only going to be what, 1? That sounds not very good. It sounds kind of slow. Well, it's kind of relative, right? But what the game designer, what the programmer can do, is they can devise essentially a multiplier, a speed multiplier for the direction. So if we want the Apple character to move something like 30 units or 30 pixels every second or something like that. So what we would do is we would get something like the input vector, and in this case, 1 directly horizontally. The input vector would be, 1, 0, because it's 1 horizontally and so on. And then you would multiply it by just a number. You wouldn't multiply it by another vector necessarily. What you'd be doing is just multiplying it by a specific number. And so if we decided 20 was the number we wanted, then if you multiply a vector by a number, then you're just simply going to come out with a vector which just multiplies the value to both the x and y components, and it works the same way in 3-dimensional space with an x and a y and a z component on the vector. So we have 20, 0, and so awesome. So now when we apply 20, 0, I want you to move 20 pixels on the x-axis and 0 pixels on the y-axis, then it can do that. And so that's really cool and that's really powerful, but here's a problem that we run into when we're dealing with movement vectors, okay? And that is that, let's say that our Apple character is being controlled by the player holding down the W and the D key at the same time, right? So what that means is that the vector, our movement vector, is going to be, can I like copy and paste this? Ooh, cool, that was kind of neat. It would be 1, 1, and so therefore the movement would be 20, 20. That sounds fine, right? It seems reasonable because you're holding the D key down, you're moving right 20 pixels a second, and you're holding the W key down, so you're also moving up 20 pixels per second. So it seems reasonable, it seems fair, but it's not actually, because what happens here, if we look back into our little coordinate space, is that this is 1, 0, let's say, this position here is 1, 0, And then this position here is 1, 0, 1. So essentially, 1, 1 would be out here. Okay. Boop, 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 boop. And so therefore the vector is like that. But do you see the problem here? The speed that you're moving horizontally is 20. That was interesting. Is it would be 20 pixels per second. That's your absolute speed that you're moving. You're moving 20 pixels per second. Also vertically, you'd be moving 20 pixels per second. But if you're moving diagonally, are you moving 20 pixels per second? Is that the length of this vector? Do we have to come back here to the Pythagorean theorem? I think we might. I don't know how to move. There, Pythagorean theorem. Well, what is that? 1 squared plus 1 squared equals c squared. So that's 1 plus 1. What's the square root of 2? Someone bother telling me. The square root of 2 is not 1. The square root of 2 is the length of this vector, which is about like 1.4. Oh gosh. So if we're moving 1 here, 1 here, 1.4, that means that the speed in absolute terms is going to be that square root of 2 times 20. Does that make sense? So the problem that we're seeing is that when you're moving diagonally, so if you just move your character diagonally, the character is moving through world space faster. And especially for a first-person perspective game, you would just be like turning away and moving diagonally toward the direction you want to move, and you're hypothetically going to be able to move towards your destination more quickly. Now, speedrunners, gamers who like to speedrun games, are very well aware of this kind of flaw in a game's design, or the implementation of the game's design. And a lot of old games kind of suffered that problem, and so a lot of speedruns you'll see is just like the character moving like diagonally, and it's really kind of silly. So what we want to do is we don't want the player to be able to move that fast. Okay, so the reason, so the solution to this problem would be to limit the vector to always be of length 1. So 1, 0, 0, 1, that's length 1, that's perfect, that's perfectly fine. But what we want is that this to be limited to length 1 also, and then this to be limited to length 1 also, and this to be limited to length 1 also. And if you kind of draw them all around, you'll see that it creates a circle. Okay, that is exactly how that works. So if this whole concept of keeping a vector at length 1 is very important inside of game development, and it has special terms. Okay, ookie. A vector of length or magnitude 1 is called a unit vector. Okay, a unit vector is any vector of length 1. And it's obviously really helpful to prevent us from coming with those problems where you're able to move faster diagonally. And in order to take any vector, so let's say like 1, 1, and to make it a unit vector, to make it so its magnitude is length 1, what we do is we normalize the vector. Okay, we normalize. When you normalize a vector, you turn the vector into a unit vector where it is length 1. Okay, so what would be the normalized form of 1, 1? Well, all that is you essentially take the length, you take you have your x and your y components, and you are able to produce the length, which is the square root of 2, and you then simply divide out the x and y components by that value. You're just dividing the length away from each of the x and y components, and then that vector is normalized. So we can do the math, and we would find, and this is where we could expand this into talking about sine and cosine, because that's effectively what this is. Okay, now you don't necessarily need to know all the math behind it. You just need to know that when you're dealing with a situation like this and you want the character to be able to move in a fixed speed regardless of its direction, you would typically what we would call normalize that vector. Okay, so let's talk about another way we would, or another reason why we would normalize a vector. So consider a game called Peggle. Remember that game Peggle, where you have like a cannon at the top and then you've got these little like circles, circle, circle, circle. Is that what they're called? I think they're called pegs, hence the name Peggle. Or maybe they're apples. These are really bad circles, okay? Someone needs to tell me. So here's the problem. Our ball is going to be shot out of the cannon, or our apple is going to be shot out of the cannon at the same power, regardless of the direction that this cannon is facing, Okay, so regardless of whether it's facing directly right or directly left, it's always going to be shooting the same power. Okay, but how is normalization helpful? Well, guess what? If you're playing it on like a computer, your mouse might be here, your mouse might be here, your mouse might be here. Okay, so the length of those vectors are all very different. This length and this length and this length are, well, hold on, what am I doing? This length and this length, they're all different lengths, but they're the same direction. And that's why when I was talking about at the beginning, how vectors are often used to talk about position, and also they're used to talk about direction. And this is what I'm talking about. The vector is now not being used to determine its length or to determine the position of the mouse in space, but rather the importance here is the direction that the cannon is facing. And we're able to essentially get that information by taking this vector, the difference between the mouse's position, the cannon's position, and then we normalize it. So the value that we get here is going to be the same, supposing that they're all parallel. It's going to be the same direction. And so when you normalize it, it's going to be the exact same vector. The result is going to be the same vector. So whatever this would be, I'm not sure what it would be, like, you know, something like 0.33. I didn't do the math here. 0. You know, like 8, or, you know, negative 0.8 or something like that. The length, I don't know, you're gonna have to do it. It's probably totally wrong, but let's say that that's a unit vector. And so it's going to be the same vector regardless of the position of the mouse. And then we multiply this by the power of the asterisk, so like cannon power or something like that. And I'm like sometimes writing with hand and sometimes I'm writing it with text. So we've got our cannon power, and then by doing that, we know that regardless of the direction, it's always going to shoot at the same cannon power because the length of this vector is always 1. Okay, so whatever the cannon power is times 1, it's going to be the same thing. It's going to be the same power. So that's part of why we use these types of, you know, normalization. We get the difference vector between the cannon and the mouse, and then we normalize the vector, and then we simply multiply it by the cannon power, which is it's just a number, not a vector. All right, but now let's talk about some of the caveats or some of the problems that we have with dealing with normalization of vectors. So let's say that we're creating a game where we have a slingshot, right? And we've got an apple, and we're slinging apples. Okay, I've never, like, you should take this idea. It's probably a really cool game idea where you just like launch something at something else. It's pretty cool. I give you permission to have that. In fact, it launches it at Peggles. So it's like we shoot a ball at our pegs, okay, and then it bounces around. It's kind of like a new way to consider the game. So here's the thing. The apple's position with respect to the slingshot's position is that difference vector that we're going to be normalizing to get the direction that the apple is going to be launched. Whee! Right? And the distance that the apple, so this is, unlike Peggle, the power of the apple is going to be determined by how far away the apple is from the slingshot. Okay, but do you have a problem? You see the problem here? If we have an apple, these are like looking less and less like apples. If like our apple's like way the heck out here, you know, because we have like a really big resolution screen or something like that, then holy moly, we're going to be launching that apple like insanely fast, right? So we got to have some kind of limit here, right? So we don't want to be able to allow the player to launch the apple that far. So what you might be thinking is, well, I should be normalizing our apple, right? So that regardless of how far away the apple is, right? Regardless of how far away the apple is, it's going to be the same length, right? So if we draw that kind of, you know, circle around here. So if it's here or if it's here, the normalization is going to essentially truncate the length of our vector to be length 1, and then we'll multiply it by like slingshot power, just like Peggle. But do you see the problem here? The problem here is that what if the apple were here? Uh-oh, what if the apple were here? If we normalize the vector, then not only is it going to take a really long vector and reduce it to length 1 so that we can get the direction. But if it's a short vector where the length is already shorter than 1, normalizing the vector will extend the vector's length to length 1. So therefore, if we were to have a game like this, and you were to normalize the vector, then what's going to happen is that the apple is going to be launched the same power regardless of how close it is to the slingshot. But let's say we wanted to be able to just have like kind of a derpy little, not very far kind of thing. And we have the same problem also when we're talking about, games such as these kinds of platformers, or games where you're able to move your character around. WASD is all well and good for like 1, -1, -1, 1, all that kind of stuff. But what about games where you have an analog stick, right? So you have an analog stick, and that analog stick can be, pushed in any kinds of different directions. But here's the thing: unlike a computer WASD where it's just like on or off, these analog sticks can be, can go just like part of the way down to the bottom, right? So totally at the bottom is like maximum, right? Input. What is this square supposed to represent? I don't know. But if we end it here, then our character can kind of like walk, right? So if we were to try to normalize the vector, then suddenly our character is always going to be going max speed. Your apple's always going to be shoot at max speed. So you see how that's a problem? So the way that we solve this problem is that there's a number of different ways to solve it, but one of the ways we can solve it, I'll let you kind of pause and think. How would you solve this problem? Dun, 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 dun. Okay, coming back. Depending on how much of a programmer you are, you might have already decided that essentially what you're doing is you're not going to normalize the vector immediately. What you're going to do is you're going to first check the length of the vector. You're going to say, is the vector greater than 1? Right? So I'll go ahead and write that down. Right? So you're trying to ask the question, if the vector applevec dot length, we're not even going to use it. It could be a function otherwise. If the length is greater than 1, then you're going to normalize. If it's not greater than 1, then we're not worried about it being launched too fast because it's not greater than 1. Regardless of its X and Y component, it's never going to be shot faster than your game's design has limited that apple from being shot or the character from moving. So you first check the length of the vector, and then you normalize your apple vector. Therefore, you're able to preserve a maximum speed, but also allow the character to have different levels of slower speeds. Pretty cool. So these are just a couple of the different things that we're talking about. We learned about normalizing vectors, unit vectors, and there's a whole lot more that we can talk about, especially when we talk about three-dimensional space and rotating around different vectors. And we're not going to be talking about that today. That's for a different lecture. But thank you for joining me today. And I hope you liked the video, and maybe you can kind of stick around and see some more videos. All right, well, signing off. Until next time.